Good morning, this is Scott Sanford. Today we're going to start the first session on a series of on irrigation management. It's a series of 5 sessions we will be doing. Plus, for those who want to participate, we'll be doing a field workshop as well. So this is the first one we're going to do today is it's on Irrigation 101. So we're going to give you a brief overview of what's required for irrigation, talk a little bit about equipment, and then we'll finish up with some economics and costs for center pivot irrigations, which is kind of the workhorse of the industry. These sessions are made possible by a grant from SARE for looking at water management. Okay, so the first things for the components of irrigation system, we need 3 things. We need a water supply, we need a way to transport the water to the point of use, and a way to distribute that water on the crops. And these pictures depict the very simplest with carrying buckets of water to a small patch and then basically splashing it onto plants. But that's in its simplest form. Today's world, we use pumping systems to do that for the most part. So the water source for irrigation can come a number of places. Groundwater, so you drill a well in the ground. That's 90% of what we use here in Wisconsin. Surface water, which would be lakes, rivers, ponds, and that's about 9% of the water used. And then we can use gray water or tea water, or basically if you're a food processor, you may have wastewater that can be irrigated onto land. In almost all cases, this is going to require a DNR permit, Department of Natural Resource permit, to use any of these water sources. So to drill a well or to use the surface water, unless if you dug your own pond, it might not require a permit to use that water, but probably require a permit to dig the pond. The next part of it is the pumping system. So this is taking, bringing the water out of the ground and moving it, or the surface water, pressurizing it and moving it some distance to the place where it's going to be distributed. And it will provide the energy usually for the distribution of that water. So this is going to have a capacity, so how many gallons per minute we're going to need, and a pressure, typically measured in PSI, or it might be in feet of head. And that's basically going to overcome friction in the pipes, and whatever's left over is used to throw the water some distance. We will need piping, and in Wisconsin we don't have a lot of surface water except for or canals, except for in cranberry use or cranberry bogs. They would use some canals for flooding, but typically in most cases we're using piping. So we need to size that to reduce the frictional losses at maximum flow rate. Otherwise that can be a significant energy user for an irrigation system. Then we have a distribution of the water. So in Wisconsin, 97% of that is sprinkler. We're going to have some furrow irrigation. So about 2% flood irrigation. We don't have any furrow in Wisconsin, but we have flood irrigation, which is basically cranberries, and then some drip irrigation, which would be largely small fresh market vegetable growers for the most part, or strawberry growers. And then typically we're going to have a control system to control this, and it could be very simple or more complex, and we'll talk a little more about that. For surface water, a DNR permit will be required. It may require filtering to get particulates out, depending on what kind of irrigation system will be used downstream from the surface water. One of the issues here is when we need water or irrigation the most is typically when we have the least amount of rainfall. So if we're requiring or relying on rain to refill a pond, for instance, that may be a problem, or if it's a spring-fed pond and when we have a drought situation, the spring dries up, that can be a problem for relying on that for surface water. Now, in some cases, we will use a pond, fill it from a well to act as a surge control. So if we need a lot of water and we have low well capacity, we might use a pond to pump water up into a pond, and then we will use it out of the pond at a higher rate to supply our water to our irrigation needs. Groundwater, some of the important things there is depth to water. So most places where we irrigate, it's sandy soils, and often the water depth is fairly close to the surface of the earth. We will need a yield or a capacity. This is typically in gallons per minute to provide water. And then we have to worry about quality. If we do a lot of irrigation, salts may be a problem. In some parts of Wisconsin, iron bacteria is a problem, and then hard water. Basically, if we're in limestone, which we have a good bit of that in Wisconsin, that can cause some issues. As I mentioned, wastewater, gray water, that can come from food processing plants, treatment plants, or it can be manure tea water. So we have some large dairy farms that filter out the solids out of the water. So if you get it down to about 2% solids, you can irrigate that on. And typically they like to do that because they'll irrigate it on when the crops can use it versus putting the manure on in the spring or fall after the crops are on and have a potential for leaching or runoff. If we put it on when the crops need it, that better utilizes the nutrients in that water. So we have a couple different kinds of wells that can be used. On the right here is or left, I'm sorry, is a driven well. So this is commonly called sand points. It's a pipe with a point on it, and we just pound that into the ground. Typically there's going to be less, when water's less than 20 feet from the surface, to do that, because we're going to typically have a pump that's going to be above the surface or sitting on the ground level, and it's going to have to lift that water out. So typically about 20 feet is the maximum you can use that type of pump with. The other type of, the most common type is a drilled well, and we're going to talk a little bit more about that, but we have a casing that's put in the ground, it's grouted in place, and the water source comes from lower in that ground level, typically. So here's a typical drilled well for an irrigation. We'd have an oversized bore, so we drill the hole bigger than we need. We drop the casing in it. We're going to put a gravel pack around the bottom here, and that's to basically it does a couple things. It filters out the sand and stuff from getting to the screens, because we have screens here, and if they plug, we'll have lower water feed. So we'll put the gravel pack around to allow better flow of the water, and then it's grouted up to the surface to seal it from contamination from surface water. So that's typical. Typical well, you might have a 20-inch or 18-inch bore, and then the casing might be 14 inches in diameter. That would be a typical well size for Wisconsin. For drilling wells, we have state requirements. Basically, it's NR 812 Wisconsin Administrative Code. Basically, it covers materials, equipment, and methods for drilling wells. It also has minimum distances to potential contaminants, minimum distance from wells, minimum distance from streams and lakes, and usually requires some bacteriological testing and analysis for the water. Some counties have the authority for this, but in most counties it's going to lay with the Department of Natural Resource. For high capacity wells, this is considered defined as any property that has total well capacity of greater than 70 gallons per minute. So this applies to all wells on a continuous property. So if you have 7 different wells that are 10 gallons apiece, that's 70 gallons. That would basically be a high capacity well. Or maybe it's eight wells at 10 gallons a minute. When you put a high capacity well in, it can't affect the public water wells by more than 10 static feet, and the DNR will determine this. The setback from streams is 1,200, or trout streams is 1,200 feet. Again, that's a requirement or the assessment that the DNR will do. The application fee is $500 for the well. The approval is supposed to be in 65 days, but due to some lawsuits, that's up to 6 months at this point, with quite a bit backlog at the DNR. If you want to, the applications are at these two websites. You can get the applications. And if you want to see what kind of wells are in your area, this last link has lists all the high capacity wells in your area, and you can sort them by county, you can sort them by irrigation well or type, but it'll list the wells, the depths. So if you've looking at putting a well, you can get a good idea of what the depth of that well might have to be for your area. With private wells, it's a lot less, so it's less than 70 gallons a minute. So if it was a small vegetable farm, maybe only has a couple acres, you might be able to get away with a well that's less than 70 gallons a minute. The fee for one of those wells is $50 to the DNR, and in some counties that's the county oversees that. So I know Dane County is one of those that oversees that. Most cases it's going to be the DNR. So a little bit of well hydraulics. So when the water is not being pumped, we've got what we call a static water pressure here, or static water level at some point. Once the well starts pumping, we get what we call a cone of depression. So the water level is going to drop in the well to some pumping water level rate, which is going to be the equilibrium between water flowing in and the pumping rate going out. So this is showing a submersible pump, be typical of a household pump, a residential pump. So the pump is down in the well, and it pushes the water up and out to the end use. A little bit of terminology: yield or capacity, that's the pump output, and it's going to be measured in gallons per minute. The pumping water level is the water level when the pump is operating at, and when we're figuring out lift of the water, that's an important factor because that's what we're going to be lifting against that pumping water level. The drawdown is the difference between the static water level and the pumping water level. So if we go back to the previous slide, this distance here, this is the drawdown for this well. So then the other point is the net positive suction head. All high capacity wells will require some number of feet above the well. So between the pump inlet, which on a submersible is on the top, so between here and where the pumping water level is going to be the net positive suction head requirement. And all pumps will have that, and we'll show you how to find out what that needs to be in a few slides here. But that's important because what it does, it prevents cavitation. If there's not enough water or positive pressure at the inlet of the pump, it'll create a vacuum and you'll get cavitation. So there's pumps. There's two types of pumps basically used for irrigation. One is a vertical turbine pump. The motor is going to be up on the surface. It's going to have a shaft that runs down to a set of bowls where the impellers are that put work on the water, and then it's going to lift it up. And I've got a slide here in a minute that's going to show you some more details on that. The other is a submersible pump, which is very common in residential houses, where the pump is down in the well, and we have the electric line running down to it. And the water, it's basically the pump is connected on the end of the pipe that brings the water to the surface. So here's an example of a electric well or vertical turbine pump. This is an electric motor here. We've got 2 distribution points coming off that and some valves in here to control which way the water goes. This one happens to be a 125 horsepower motor that feeds a center pivot. Here's some diesel powered generators or diesel power driven. So here we've got our diesel power unit. We've got a shaft here, and we've got a right angle drive that drives the shaft that runs down to the bowls. So there's a shaft that runs down through this. Here's a homemade one down on the lower end here. This happens to be very oversized, so they're using more energy than they need. But one of the reasons I put this on is because this has a generator on it, electric generator. The towers on a center pivot require electricity to run. So this one has an electric generator to provide that electricity to power the motors that moves the pivot around the center pivot. The other important thing here, this one here has a shield over the shaft, whereas this other one is minus the shaft. So that's a safety issue. That this, the one in the upper left, should have a shield over the shaft. So here's an illustration of a vertical turbine pump. So here we have a bowl. This would be considered a bowl here. These sections, I think it actually runs from here up to here, but that would be a bowl. And this one's made up of 3 bowls. That's very common to have a number of different bowls stacked up. So the water comes in the bottom, up through the first impeller, puts work on it. That's the input for the second bowl, and work is put on that, on up through the third one, and then it heads up to the surface through the pipe that's attached to. And the shaft running that comes down from the surface. So here's on the right here, we've got a picture of the motor with a shaft running down to the bowls. This shaft will have some supports or bearings to hold that. They're either water lubricated or they will be oil lubricated, depending on the type of on the manufacturer. So that's how they work. They're going to have a number of different kinds of impellers and stuff on these. Here's an example of a 2-stage pump with arrows on it, so you can see how the water pattern comes. It's going to come in the bottom here, up through this impeller, out, work on it, up through, next impeller out, and then up to the surface. And you can see the shaft running down through that. The other type of pump we can use is a submersible pump. So on the right here we've got a picture. The silver part, that's the motor. Nice part about a submersible is that the motor is water cooled in this case. We've got an electric line running in here. This is our inlet screen. And then we have 1, 2, 3, 4 bowls on this to provide our capacity and pressurize. So the electric has to be waterproof in these. And one disadvantage, if the pump fails, although they have very long life, but if the pump fails, you got to pull the whole thing out of the well to service the motor. These are our multi-stages I've shown you, and they can have very high pressures and flows, up to 1,700 gallons a minute. The other type of pump it's used typically on surface water is a centrifugal pump. So these basically, this is showing the right here a cranberry bog. So we've got 3 pumps here. This is the suction out of the surface water, and this is I believe electric motors over here driving the unit. On the right here shows a little better. So we've got the inlet. Well, actually, this is the inlet here, and this is the outlet going out this way to whatever use. We've got a pressure gauge right here, and it's going to be electric motor. They can be tractor driven, they can be engine driven, or in this case, is motor driven. They also can be self-priming or non-self-priming, and there's the difference. Well, the self-priming is easier because you flip the switch and they should prime themselves, but they have a lower efficiency versus a non-self-priming has a little better efficiency, and we'll show that in a minute. So here's a pictorial of the guts of a centrifugal pump. We've got the inlet here. This is the impeller in the middle. It's going to exert work on the water and go to force it out the discharge as it puts work on it. So here shows this is a graph of the we've got across the bottom here we've got the different kinds of pumps, and up the side here we've got the efficiency of the pumps. So we've got the first one is a high head or high pressure centrifugal pump. So they can go from about 55% efficiency to 70% efficiency. We drop the pressure, the efficiency would go up by about 5%, so we go 60 to 75 roughly. Non-self-priming is going to start at that 65, but it's up a little bit, almost to 80 on the high end. That's for high pressure. The medium pressure non-self-priming could be upwards of 80%. Submersible is going to start at about 65 and go to about 85, and the vertical turbines are going to start at about 70, 75 and go up into the mid to upper 80s, just as an example. So that's one of the reasons why we use vertical turbine pumps typically, is because they're higher efficiency. Here is a pump curve. Every pump will have a pump curve. So I want to go through the different things you can get out of this. So up the side here we've got the feet of head, or you can convert feet of head to pressure. It's 2.31 feet of head per pound per square inch. So that's an example. This particular one, can you have a range of impeller sizes in it? The one that we're using is 8.5176 inches in diameter, and if we follow that around, this was designed for 1,000 gallon per minute, which is across the bottom here is my gallons per minute. So 1,000 gallons per minute. So my operating point is going to be right here. So it's about 175 feet of head, at 1,000 gallons a minute. And at that point, it's going to have an efficiency of close to 85%. These green lines up here, those are efficiencies. So I've got 85% there. It's a little less than that. This is 83. So it's going to be, 84, 84 and a half probably, somewhere in that range for efficiency. The other thing we've got down here is net positive suction head required. Previously I said we have to have a certain amount of feet of head for the pump to work. So here's where it's going to be. These are, so I got 0 and 25, so this is 12 and 12.5. So this is maybe 13 feet of head here to run that. The bottom line here is gallons per, or brake horsepower, which is over on this side. So we got 40 and 80. So this line here, this one that's not numbered, is 60. So I'm going to be about 55 roughly horsepower to run this pump at 175 feet of head at 1,000 gallons a minute. Now, one thing I want you to also look at, if we drop the head, now one of the ways we can save energy on irrigation systems is to drop the head. So if I went down to 150 feet of head, this pump is now going to operate over here. So it'll operate over here, and we'll talk more about that in a couple of weeks. So it's going to operate almost at 1,200 gallons a minute. So that's one of the issues we have to contend with. If we drop our pressure, our horsepower went up in this case, and more importantly, the net positive suction head requirement went up too. So that pump is going to have to be covered by more water to work properly without cavitating. Capacity and pressure. The capacity we need will depend on the maximum ET. Here in Wisconsin, our maximum ET is about 0.3 on the hottest day of the year, and we usually have an application efficiency of 90 to 95%. So that's going to give our overall requirement. We're going to need to replace water at about 0.33, 0.35 inches per day to satisfy what the plant's going to use. Well, if you calculate that out into gallons per minute, it's going to be 6 to 7 gallons a minute per acre of land, and that's pumping 24 hours a day. So if we only wanted to pump 12 hours a day, it's got to be double that. So it'll be 12 to 14 gallons a minute. So that just gives you an idea of the amount of water we need. So the other thing is the pressure. Pressure will depend on the distribution type. So if we're using traveling gun, which has a high pressure requirement, we could be 100 psi plus. If we're using drip irrigation, which has a low pressure requirement, 20 to 30 psi. In fact, we can actually do drip irrigation on very small plots using just gravity if we get the tank high enough. Typical center pivot's going to run on 40 to 80 psi depending on the nozzle selection that we're going to do, whether we're going to run it at a higher or lower pressure. So the next thing I want to do is go into the types of irrigation systems. So in the top here we've got it's a center pivot. The one to the right of that is a traveling gun. Down in the lower left is a movable sprinkler system or hand move system. These pipes can also be buried in the ground, and then we call it a solid set system. And then on the picture with a pipe here with the water running out of it, this is used in furrow irrigation or surface irrigation, and we're not going to talk much about that. We don't do any furrow irrigation that I'm aware of in Wisconsin. We do some surface irrigation in Wisconsin. It basically is flooding cranberry bogs. That's basically the only place they're used. So with hand move system or solid set, We've got a lot of pipe here, and my initiation to irrigation was moving pipes for a hand move system, and we'll have some sprinklers or risers coming up, and the water gets going out and these spin around. Typically they're an impact sprinkler that's going to spin around. These will require a layout in a set pattern depending on the sprinkler and pressure to get uniform irrigation. So typically they're put on some kind of a grid pattern. It might be like a 40 by 60 pattern or 40 by 40 pattern to get the proper coverage for those. So this would be your main line here, and these would be your laterals going out. So it might be 60-foot spacing in this direction and 40-foot spacing in this direction with some overlap in the middle. So you'd have overlap between sprinklers to get your even coverage. Up in the upper or up in the top picture, that's basically so on a solid set system where the pipe is buried in the ground. We've got nozzles that the grower would go. They're either pop-up nozzles or you'd go around in the beginning of the season and you'd set them in there. And then if you have to do any tractor work where they'd interfere, you'd pull those out to do your work. Here's an example of a system in a bog with solid set sprinklers. The other place I use solid set is on golf courses. So this kind of shows the layout of a golf course. So here we've got a green space, and we've got the lateral down the side here with 3 sprinkler head mounting points out of each of these. One of the unique things of golf course is we never have all these going at once, and we could have any number of them going at once. So they typically will have a very more complicated pumping system because it has to be able to accommodate different capacities based on the number of nozzles that are being used. Another system is a side move system, and this has got to be a farmer that put this together because he got sick of moving pipes. So the pipe is put on a wheel that can be rolled. These don't just run down the field. It's actually what we'd call a move and set. So if you look at a little illustration on the bottom, we've got the main line pipe running along the south side of the field, and then we'd set it, we'd sprinkle, then we'd move this forward, reset it, hook it up to the main line, sprinkler again, and we keep doing that down the field. So, every hour or two you'd go out there and move the pipe to cover your system. So these systems are great for low height crops. Typically they're used out west a lot for alfalfa. This field here is a potato field in the upper left there. They wouldn't work too well in corn. This one to the right is corn. I suspect they're using that to get it germinated, and then they let it go on its own after that. But these still require labor to move, but a lot less than a hand move system. The next type of system is a traveling gun. These are kind of nice because they can be moved around to wherever you need them, as long as you can get a water supply to them. The disadvantage, they higher energy costs because they require higher pressure to operate. Basically, the pressure is used to throw this water out some distance. They are portable. It does require labor to move, but we do have to have lanes. So we've got this area where we lose crop production because we have to lane for this traveler to get pulled back to the reel. And as it pulls back, it keeps flipping around and watering the territory. So that's a disadvantage, but they're very flexible, the fact that you can do odd-shaped fields or corners of fields, etc. The center pivot system is a workhorse. A typical center pivot system would be set up as a quarter section system, although they can be different sizes. So they would cover, a straight system would cover 130 acres out of the 160 acres of a quarter section field. Little terminology: if they rotate all the way around, they're called a pivot. If they're only do like halfway, say they're set up on the edge of a field, so you might have them down a field like this, and the pivot's here, and it goes out like this, and it basically comes around and back. That's called a wiper. So just a little terminology of how these are classified. But it's the same equipment either way. So we're going to talk more about each of these pieces of this system. So we're going to start with the center pivot, or the center of the pivot, I should say. So this is where the water gets fed in. So down here is the water supply coming in. It goes through a riser pipe, through a pivot section, and it's going to go out the lateral to the different sprinklers. These run on electricity. The towers run on electricity, so we've got a slip ring here to provide the electricity out to the pivots, and the control box will be located at the center pivot. So this shows the control box, and they'll have an hour meter, an amp meter. Probably the most important thing is this device here. That's a cycle timer. That's a percentage of time that the last tower motors will run, and that's the only tower that we control on a center pivot, just the last one. All the rest of them are set up on limit switches to try to keep up with that end tower. So this is usually a 2-minute cycle timer, so every 2 minutes it would be moving some portion of those 2 minutes as we go through the field. The center pivot frame is typically anchored to a concrete platform. They do make portable ones that are on wheels, and I believe they still have to have some kind of a ground anchor to keep them centered from moving. So the next piece up the line is going to be a tower. So this unit here is considered a tower. It's going to be the joint between two laterals. It's going to have a motor down here. I'll show it to you over in this picture. So we got a motor here with a shaft that goes to a gearbox at each motor. So there's a gearbox here that runs the wheels or to move the unit forward and backwards. Up on the top of the pivot, so right up here is where this is a limit switch, a cover for where the limit switch is. This is a rod that comes from the next section of pipe. So what happens as the sections get out of shape, so say this is a tower motor here, and here's the end tower here. As these get out of kilter, the limit switch will kick in, and this will move. So, you know, once it moves, it will be someplace like this, trying to keep up with that end tower. So they may come on, so this one will come on, then it forces the next one out of, clicks the limit switch to the next one, it'll move up. So it keeps, they don't move necessarily in a smooth pattern. They kind of move a couple feet and stop, move 2 or 3 feet and stop as they go up the field. The tower motors will have a motor. These drive motors will be anywhere. Typically it's about 1 horsepower, but they can be anywhere from 3/4 to 2 or 3 horsepower. The next thing is the span, or the lateral that moves between towers. So this is what the sprinklers are attached to. The sprinklers can be on top of the lateral. So here's this is an impact sprinkler that we've got here, or they can be dropped. So these picture in the lower right is showing drops that come down, and then the nozzle's actually on the bottom of the drop. So these spans can be 100 feet to 250 feet. Sometimes the first section is a little shorter than the rest of the sections. It just depends on how they're laid out. A typical center pivot's about 1,300, 1,310 feet long. It just depends on the size of the field as to how long the total system will be. This one over here is showing a drop nozzle. The object of a drop nozzle is to get it down closer to the ground so it spends less time in the air to reduce both wind loss because of wind and loss because of evaporation. Here in Wisconsin, we don't have a lot of evaporation loss. We can have wind loss, but typically not a lot of evaporation loss. The other thing is that this nozzle needs to be above the crop canopy unless the crop is planted in a circular pattern, and the nozzle is meant to be in the canopy. And typically you need about 3 feet between the end of the nozzle and the top of the crop canopy to get proper distribution of the water. So that's an important factor. So if you're using them for things like corn, you might want to look at just using nozzles on top of the system. If you're just using them for veg crops that are low, then you might want to consider drop nozzles. On the end of each system, a lot of times there's an end gun. That's this out here in red, so that's the end gun. And this section here is called an overhang. The overhang can vary in length from 10, 20 feet to up to maybe almost 100 feet, depending on the system. Typically in Wisconsin, they're not that big, but typically we'd have an end gun on the end of it. Not all cases. So the end gun is basically needs to run at high pressure or higher pressure. So if we have a low pressure system, then we need a booster pump. So this picture above the end gun showing the booster pump that's going to bring it from, say, the 40 psi up to 60 to 80 psi so that the end gun will perform properly. So that's the end of the system. So then there's two different kinds of center pivots, and we'll talk about corner systems. So the left picture here is a straight system. So we've got a straight system that runs around. Occasionally, if the end gun comes on, it might cover a little more ground here in the corners, but typically it's just going to go around, and we'll get about 130 acres out of that 160-acre field. Now farmers, they like to cover as much ground as possible, so somebody came out with a corner system. So this has an extra arm on the end here that'll fold into the corner. So when it's at the narrowest part of the field, that corner arm is folded back, and as we come into the corner, then that arm starts to open up, and different numbers of sprinklers will turn on and off depending on the position that arm is going into the corner of the field. So here's what they look like. So on the right here, this is the end tower here for the straight part of the system, and then this is the corner part of the system. So again, this is the end tower for the straight part of the system going this way, and this is the corner system with an overhang on here and an end gun out here. So just to give you an example. So the advantage of this is that we can cover all but about 4 to 6 acres, so we get more land coverage on that. Although this section is higher cost. To put one of these in, this one little section is about $40,000. and we'll cover more costs a little later. They do need a guidance system, and it will affect uniformity, how uniform the water is distributed on the whole system when these turn on and off, depending on the manufacturer. But it's not going to be, it throws off the uniformity even on the best systems. Whenever you're watering more land, you'll have to have a higher well capacity to cover that ground. So here's shows kind of some of the controls. We can turn nozzles on and off. We've got the end gun to turn on and off, and the ground speed sometimes is controlled. To get these things to go into the corner, sometimes you're using a GPS antenna type thing. Sometimes it's learn mode, so it knows that the main part of the system is at 0 degrees compared to some home, or 90 degrees or 45 degrees, and it knows, depending on the number of degrees of rotation, where it should be in the field. Some of them are follow a buried wire, but in all cases we've got these guidance systems. So this is a steering system here to steer these wheels to make this system go into the corner and come out of the corner, depending on where it's positioned in the field. Another type of system that's similar to a center pivot system is called a linear move system. And you can see this looks the same as a center pivot system with towers and stuff, but the difference is this moves straight down the field. So it's great for rectangular fields, because it'll cover the whole field without any unirrigated corners. It does require a hose to be dragged, so it's a little hard to see, but this picture here, there's actually a hose that comes in the back side of this, and it will have typically a gasoline or diesel engine on here to drive this system. And then the guidance system, it's either going to be a follow the wire or a trench. So this one here, I don't have a good picture of it, but it actually has a trench that runs down here that has a follower wheel that goes in to keep it going in the direction you want it to go. Otherwise, this works the same as the regular system. So this first tower is the driven, so this is the driven system on the big picture up here, driven end. And as it goes down the field, there's limit switches, and the rest of these towers just try to keep up with the driven part of the system. Another adaptation to a traveling gun is a boom system. This one actually I found in Ohio, but just to keep you informed of what's out there. These have more uniform application, so that's good if you're doing veg crops. Basically, they can run at low pressure at the boom. It's low pressure. They can fold up, so this is opened up. So we can put more of a sprinkler type system on here that will not have very big droplets for more fragile crops, and then it folds up for transport. So that's just showing an example. But it does use a reel system, so we're going to have a hose running down the field, and it's going to require higher pressure than a center pivot system would go. But just an example of another type of system. I don't know that there's any here in Wisconsin, but another type of application. The last one we're going to talk about is a drip or micro irrigation system. The biggest advantage of these is it basically can save you up to 50% of the water that you'd need to water a crop otherwise. Basically, you're just watering under the plants here, so you'd have a wetted area, you know, something, some side and depth under the plant. Otherwise, in between the rows, so this area in here would not have to be watered to keep the plants growing. So the trees up here in the left picture is a good illustration. We've got a we're watering the root zone basically, and the rest of this is dry. We're not going to water that. We're going to let rainwater cover that, but we're not going to water that because it's not needed for the tree, keep the tree growing productively. So that's just an example. Typically, these are used more on veg crops than anything. Now, an adaptation of that is to bury that drip line in the ground, and this is called subsurface drip line. So here's an example. On the left here, we've got drip lines. They're permanently put in the ground. These would be, so we'd plant our corn rows so that they'd straddle this. So we'd have a drip line here, and we have a dry location between drip lines. So these are typically put in permanently. Costs can be fairly high, $1,000 or more an acre to put these in. And one of the issues with these, if there's a damaged spot, sometimes they're hard to find until things aren't getting watered correctly. In the upper corner, this is showing how you might put a drip line into a potato hill. So you put the drip line in above the seed piece, and then the water will come down because your seed piece is going to be the root, and it's doesn't have very long-reaching roots. It can't go deep like a corn crop can. So you might do. Now, some cases when we have a subsurface drip, we still may need some irrigation from overhead for germination until that crop gets to where it would have roots to reach down to get that water from the subsurface drip system. Sprinkler nozzles, impacts are the one that's been around the longest. They require higher pressures, but they have a bigger wetted diameter, which has advantages from an instantaneous rainfall rate. So they can run on 25 to 80 psi, and basically at lower pressures it won't throw the water as far as it will throw it at higher pressures. End guns and big guns. So a big gun would be like what we'd use on a traveling gun system. They'll all require more pressure, and the higher the pressure, the farther we can throw the water. Also, the higher the capacity that's being pumped through there will require higher pressure to throw the water as well to get it spread out. Then we have spray type nozzles. These can be classified as a fixed plate, rotational, and bubblers. I don't have a picture of bubblers in this, but basically it's a drop nozzle that hangs down to just above the ground and would just dribble water on the ground as it swings around. So it takes very little pressure to provide that. So here's an example of a picture just trying to illustrate the fact that higher pressure throws the water further. So if I lower the pressure, so we're getting the same amount of water out of this. So if this nozzle is putting out 100 gallons a minute, it's the same amount, but if I cover less area, I'm going to have a higher application rate on a per hour basis, but because I'm lower pressure, I've reduced my energy costs. So when we're looking at lower pressure, we have to look at topography and the type of soil and the infiltration rates of the soil to decide what pressure to use based on basically the throw distance and the infiltration rates of that water. So on the impact sprinklers, this is kind of what they look like. They've got an arm here that flips back and forth that has a weight on the end. This provides the impact to basically rotate this. You've got a bearing down here. Some will have nozzles out of both ends, so the one out of the back end smaller to cover areas close to the nozzle, and a larger spray coming out of the end with the impact arm on it. The lower the trajectory of these, the less issues you'll have with wind. And also the larger the droplet area out of a spray nozzle, the better it will fight wind, but a larger drop is more harsh on new crops. Spray nozzles come in a number of different sizes. They can be used on a solid set system. They can be just as fine mist coming out, etc. So we're going to go, next picture shows a little better. So in the upper right here, this is what we call a flat plate or spray nozzle. The water's coming down, hitting a flat plate, and then going out to the sides in a pattern. So this puts out a donut-shaped water pattern. It works fine on a center pivot, but it would not work on a solid set or a system that doesn't move. Moving over to the left, this is called a spinner, and you can see it's putting water out in all different directions. This has a nice even pattern of water to spray out, but it doesn't cover as much ground as the next one, which would be called the rotator, which is on the bottom here. This will have 2 to 4 streams of water coming out. It covers a larger area than either of the first two, but it again puts out a donut-shaped water pattern for the most part. So it works fine on a center pivot, but might not work as well on a solid set system. And then down in the lower right is what we call a nutator. So this is a combination of a number of different, of the spinner and the rotator. Kind of goes around, puts out some bigger water droplets, basically to fight wind in many cases, and provide a more even water pattern. If you got a question on which type to use, the different companies have selection criteria to help you choose, or your irrigation dealer would be a good choice depending on the type of system that one uses. So controls. We can manually control a system. If we're doing a lawn sprinkler, we put that out, we turn it on, we hopefully set a timer, we come back and turn it off or move it. The next step up would be some kind of a timer or valve. In the lower right side, this is a simple timer that basically after a certain amount of time it would turn on and off the sprinklers or water system based on a set time. You can turn it on and off at a certain set time, or you can turn it on manually and it'll run a certain set time and turn off. So just an example of a simple system. This could be used on a small drip system. We can also use soil moisture sensors to control when the water comes on and off. So if we have low soil moisture at the sensor, the system would be initiated to come on and provide water. We can use irrigation scheduling to determine when we're going to do that. So next week we'll be talking more about that, and we can have that system so if we're less than our optimal target, the system would come on and provide water. And we may do that manually, make that decision, or could be automatic. And then in many cases we're using some kind of combination of these, because a lot of times we want to look at the weather forecast as well before doing that. Then we can use with GPS positioning and GPS things, we can do what we call variable rate application, where water is put on at different points of the field at different rates across the field. They can be blocked out by sections in the field, either in pie shapes or a little block at a time. Typically where variable rate application works the best is going to be where you have lots of variation in the soil types. Here in Wisconsin, we typically irrigate sand soils, so we don't have a lot of we may have a couple different types of sand in that field, but typically the water holding capacity is pretty darn close between them, so we're not going to necessarily gain a lot out of variable rate. Where you'd save the most is like in Nebraska and Kansas, where they have to irrigate regardless to have a crop, so they could have clay, they could have loams, and there may be multiples of those in a field. That's where you're going to save the most, basically trying to not overwater an area to allow room for rainfall. And then for a control system, we can have, this would be a complete system. We have a weather station with a rain bucket. We have soil moisture probes. We might have a soil temperature probe. It can be cell service to a receiver or to some kind of mobile device, and then maybe to your office computer where you can get the data on the system. And basically we have people that can drive up to a system, push a button on their smartphone, and the system starts and moves. Or you can do it from your office. You just want to make sure there's nothing parked in the way. So a little bit about cost. Irrigation systems costs. First, we need a well. So this would be this is based on in the Spooner area, but it'll give you an idea of some of the costs. So we might have we'd have to dig through the first 100 feet up there, which would be about $18,000, so about $180 a foot to get your well started. Once they hit rock, it's $55 a foot, and we might have a well depth in that area of 250 to 300 feet deep. So that would cost another $26,000 to get through the rock, and then we have to have a pump. So if we put an electric pump, that's $15,000 for that, with a well capacity of somewhere between 9,000 and 12,000 gallons a minute, or 1,200 gallons a minute. So my budget on my well is going to be $50,000 to $60,000 roughly to put a well, based on this. Now, Central Sands area, they'd probably be quite a bit less because one, they don't have to be as deep, and two, you're typically not dealing with much rock. The center pivot itself for this is for a 7-span with end boom, end gun, about 1,300 feet long to cover 130 acres. That's going to be about $60,000. If we had a smaller field, say a 40-acre field, that would be between $38,000 and $40,000. So you don't save a whole lot by going smaller. It's still considerable costs there, and higher cost per acre. Then you have add-ons. You want, type of sprinkler, whether you want impact sprinklers or low-pressure nozzles, whether you want drop nozzles. If you need a booster pump for a low speed. Telemetry, so you want to be able to control this from your office. There's a cost to that. Touchscreen computer instead of electromechanical. So all those are add-ons to a system. Then there's tire options. If you have muck, you might need different types of tires. And then corner system or an arm system, it's $40,000 additional. So for a straight system, we're looking at somewhere between $60,000 and $80,000 for the straight system. With a well for a straight system, we're looking at somewhere between $120,000 and $140,000. So about $1,000 an acre is what it's going to cost us to put that system in. So I'm kind of jumping here. We'll come back to how we rationalize that in a minute. But so a little bit about energy costs. So I did take in a typical system in Wisconsin. Typical system is 90-foot pumping level, 75% well efficiency or pumping efficiency. I did this on single-phase power just because it's easier to calculate. So it's 12 cents a minute. This is done on $3.50 diesel, which was a year ago, not this year maybe, but a year ago. High pressure 70 psi at the center pivot versus 30 psi. And we're going to have the end gun on 50% of the time. We're going to apply 10 inches of water with a 90% application rate. So those are my assumptions. So here's the electric cost, just to show you what the electric cost would be. So for a high pressure system, I'm high pressure versus low pressure, I'm going to save about 23% in energy costs. But you can see this is going to cost about $7,000 for a high pressure system, about $5,500 for a low pressure system to provide the power to put that water on. At $3.50 a gallon, my cost is about double that. So with diesel prices coming down, it's going to be somewhat less than that, but still there'll be this savings between high pressure and low pressure. So typically electric's going to be cheaper to run than a diesel generator. But some of that depends on whether the electric company has, whether they have on-peak, off-peak rates or not, and if you have to use those. How do we look at the economics of a system? So basically the way to justify the cost of these is looking at the yield between non-irrigated and irrigated, and that can be quantity and quality. So you have to look at those cost differences to see what the difference. So difference between dryland corn and irrigated corn, or potatoes that weren't irrigated and potatoes that were irrigated. So in something like potatoes, there's going to be a big quality difference. In something like corn, there may or may not be as much of a quality difference. It may be kernel size difference, but just that has to pay for that $1,000 an acre cost for the irrigation system, plus the energy costs to operate it and apply the water. Other uses of irrigation can be frost control, so things like strawberries and grapes use frost control especially during budding. For cranberries during the heat of the summer, they often use them for cooling, especially for dryland cranberries. And then we can do fertilization or herbicide applications through the irrigation system. This is basically under the term of chemigation. And there are requirements for those. If somebody wants to do that, there's some special requirements for that to do those. But those are some other uses of irrigation that would help with crop thing. So here's a list of resources. This first one is a book from Midwest Plan Service. Here's a couple PDFs you can download that are about selecting irrigation systems. There's a spreadsheet that we'll talk about more next week to doing irrigation water management. And here's some other resources down here for USDA, and University of Nebraska has a nice website with lots of data. So that concludes what we're going to talk about today. A reminder, next week we will be covering soil water management and the basics of irrigation scheduling, and then we have 3 more after that talking about different aspects of irrigation. So with that, we'll wrap this one up and we'll entertain any questions.